Thank you all for coming and for the invitation. Also, Matt, I see you in the call too. So hi, Matt. So this will be a two-part talk. In the first half of the talk, I'll try to give you a flavor of the work we do in my university group. And then depending on how much time we've got left, I'll switch gears and go into the second part of the talk, which is where I tell you about some of the work I do in the self-driving vehicle industry with a company called 5AI. So I'll get into the first part. Here's a picture of the group. It's a subset of the people. We're about 14 or 15 people specializing in developing machine learning algorithms for autonomous systems control. And we have a lot of work in the multi-agent space. So in a one-slide summary, what we're trying to do in this university group is to create autonomous agents which can accomplish goals in complex dynamic environments. And here are three example applications that we have actually built. So on the lower left, you have a large commercial warehouse, and you have a fleet of tens or hundreds of robots, and they need to collaborate in order to manage, physically manage the warehouse. And in our case, we also have human co-workers. So we have a test facility with a very large industry player. And in this test facility, we use reinforcement learning algorithms to optimize these systems. And the second picture is self-driving vehicles. I hope to tell you a bit more about that later. And then the third picture is meant to represent more classic teamwork kinds of problems that are investigated in this type of research. So what all of these applications have in common is that there's not just one decision maker. There's a group or a collective of decision makers, and they need to coordinate their choices in some important ways in order to achieve their tasks. So we call this a multi-agent system. Again, here's a one-slide summary to explain what this means. I'm assuming most of you will know this already, but just in case, this is useful to bring everyone on the same page. So a multi-agent system, we begin with an environment. This is the circle here. The environment can be a software-defined environment, like a computer game or a trading market, or it could be a physical environment, like a warehouse, for example. And so inside this environment, we have these agents or decision makers. The agents are defined, first of all, by ways of sensing information about the state of the environment. And they also have ways of modifying the state of the environment, so they can take certain actions. And what makes these multi-agent systems really interesting is that these agents, they need to coordinate their choices in order to achieve their goals. So their goals could be perfectly aligned, which means they have a teamwork task, and they work together, or they could be opposed. There might be opponents in a game, for example, or it could be anywhere in between too. I mean, in any of these cases, though, coordination is the key aspect. So this is useful for various reasons. Multi-agent systems methodologies can be used to address all kinds of problems. And I like to use this slide because it allows me to explain the two primary research agendas that we pursue in this university group. In the first category of research, we control one agent, which I've now highlighted in blue, and the other white agents, they are not controlled by us. So they have different organizations that control them. They may be previously unknown to us, and we have to interact with these other guys. So there's a lot of really interesting questions you can ask. For example, how can an agent collaborate with these unknown other agents? And the kinds of questions we look at include things like, we want to be able to recognize the goals of the other agents. We want to be able to predict their future actions or trajectories. And we want to then take these predictions into account when we make optimal choices or when we plan. How can we integrate these predictions into our decision-making? And we're also interested in producing systems that give us some ability to make sense of what's happening. So interpretability, or even verify subcomponents if they're safety critical. So autonomous driving is one classical example of this. This is the first category. In the second category, we control all of the agents. So I now highlight all of them in blue. And now we ask questions such as, how can they all learn together to solve a particular coordination task optimally? So coordination and communication are important aspects here, but also efficient scaling to many agents, how to deal with dynamic team compositions, and even transfer related tasks. So how can a team that was trained in one particular task be transferred to do a different but related task? So here in this example, we would have the warehouse example. And so you have a large group of agents that need to coordinate their activities. So over the next 10 minutes or so, I'll give you one example for each of these two categories to give you a sort of a flavor of the work we've been doing in these two categories. So we start with the first category, which is when we control one agent and the other agents are controlled by someone else. They have their own policies. We don't know them ahead of time. And they may not share the same sort of protocols and standards with us. So this is a paper that was published in 2021 in ICML, and we've done subsequent work since then. It's under review at a few different places. This is funded by a large grant by the US Office of Naval Research. But basically, the idea is that we have this team. And in here, we again have an environment which is the circle. We have the agents, which is the square, and we have the agents, which are the circle. We have the gray agent, which is controlled by us, and we have these other white circles, which are the other agents. So the idea is we now own a problem which we call AdTalk Teamwork. AdTalk Teamwork means that we want to be able to create this one gray agent that can quickly fit into this existing team without knowing ahead of time who they are or how they make choices. And essentially, we're thrown into this team, and we now have to adapt to this team very quickly on the fly and find our role within this team to maximize the performance of the team. In this particular work, we've thrown in a new aspect in this challenge, which is openness. So we now allow agents to leave or enter the environment at any point in time and without prior notification. So this is represented by the agents at the top here, which may leave or enter. So this could be things such as asset loss in a sort of defense setting, or have reinforcements. One classic example that I think a lot of people can relate to is something like soccer. I don't know if you call it soccer or football, and soccer in the US, where you might lose robots because they get damaged or they get taken out of the match because they've violated some rules. So whenever this happens, you have a new team composition that can really change the kind of role you need to take within the team in order to help the team win the game or maximize performance. And not only can the agents enter and leave at any time, which dynamically changes the size of the team, but these other agents may also have different types of ways of making choices. So we say they have different types. So it's a really complex teamwork problem. And we have to create an agent that can quickly make sense of the situation and dynamically adapt to these continually changing situations. So we try to solve this with deep reinforcement learning. And in a nutshell, what we're doing here is to combine a model called graph neural networks with deep reinforcement learning techniques. So here's just a summary slide about graph neural networks. It's a really interesting type of model that has received a lot of attention in recent years. And if you haven't come across, I'd recommend checking it out because they can be used for a lot of interesting applications. So graph neural networks are a deep learning style model that essentially you can train, and it uses internally a graph representation. It takes a graph, it does some parsing inside, and then outputs an updated graph. What makes it really interesting is that you can train this kind of model, and then after training, you finish the training, you can dynamically resize the model, and it can still give you meaningful outputs. So this is a really interesting property that we want to exploit here. On the right, I'm showing you again this image earlier that represents this open AdTalk teamwork problem. And I can essentially think of this as a graph now, which are the red edges. So the squares, the circles are the agents, and they're now represented as nodes in the graph. The edges are connecting these nodes, so they make up the graph. And you can think of these edges as representing relationships. So in the GNN, you have so-called attribute vectors, which are just numerical vectors that can carry information in these edges. For example, their relative proximity or certain teamwork relationships. You also have attribute vectors that are associated with the nodes, which can give you localized information, such as their local position or battery level or something like that. And the interesting thing is that you can train this graph. During training, you can add and remove these agents, which corresponds to adding and removing nodes. And then when you're finished with the training, you can essentially, again, take these agents out or re-enter them and still get meaningful estimates from the model. And in reinforcement learning, we want to exploit this ability by using these kinds of GNNs to as the the action value representation. If you understand reinforcement learning, so the standard approach is that you have a fixed length vector input, which is quite difficult to use when you have an environment where agents can enter and leave and sort of the size of your environment changes. And the naive approach would be a padding, right, where you have a sort of a zero padding. But we want to go beyond that and have a model that can actually sort of flexibly grow and shrink with the environment. So that's what we do. We use graph neural networks and we integrate them into deep reinforcement learning. So sort of a one-line summary. Here's a slightly more complicated version. So this is the actual method that we propose, called GPL, graph-based policy learning. And it consists of three main parts, which I'm going to explain in high-level terms. I'm not going to go into the deep technical details. I just try to give you a sense of the questions that we're answering here. So first, we have the green box, which is on the left here. The idea here is that we don't know ahead of time who these other agents are, and they have these unknown types. Types is just what we call their policies, basically their ways of making decisions. And in this case, we're using LSTMs, which are a kind of recurrent neural network. They take as input the sequence of observations that we make, and then they give us an embedding, a vector, that hopefully gives us useful information to identify who these other agents are. So there's nothing really new in this green part here. We're mostly just using off-the-shelf sort of LSTMs to train the agent identification. The more interesting thing is the subsequent two parts that use this type information. So first, there's the red box, which is the joint action value model. And the question that we answer here is how good any particular combination of actions is between the agents. So let's say we have three agents, and agent one can take a particular action, agent two and agent three. For example, one agent goes up, the other one goes down, another one goes left. And the question is, how good is this particular combination of actions in this particular state or a point in time? And in other words, we want to assign values to the joint actions. And the way in which we do this here is by using GNNs. So this is indicated by the edges here is essentially a GNN. And we have a particular decomposition or factorization called a coordination graph. This has already existed for a while. It's quite useful here. And basically, we use GNNs as the model that trains these value estimates. Now, this alone is not enough for us to make choices because we only control a single agent, but here we have value estimates, which are for combinations of actions for all of the agents, but we don't control the other guys. So that's why we have this third model now, which is the blue one, the agent model. Here, we're trying to make predictions about the probabilities with which the other agents choose their various actions. We can learn this from the same data as well. The reason we require this is so that we can marginalize them out from the joint action estimates. And that's shown on the right side here. So we have these probability estimates. We use them to marginalize the other agents away from this joint action here. And then we get this estimate for just our particular agent, which is agent I. And from here on, we can just use a standard RL methodology, for example, epsilon greedy. That's basically the whole pipeline here without going into too much depth here. Let's talk about evaluation. So we have tested this in various environments. Here we have three 2D sort of navigation spatial environments, level-based foraging, Wolfpack, and FortAttack. Without going into too much detail, basically in all of them, there's a particular team. We control one of the agents in the team. The other agents have various possible types that we don't know ahead of time, and we need to work with them to solve a task. So, in FortAttack, we are the attackers. We need to reach this fort that's being defended by these blue and green agents, and they can try and shoot us down. So we have to have some smart techniques to evade them and get to the defended fort. An agent can enter and leave. For example, in FortAttack, we can get shot down, and then they get sort of a penalty break, and then they can re-enter at some point. Results. So first, training. In training, we train this with teams of up to 3 agents. And these 3 graphs I'm showing here correspond to the 3 different environments that I just showed you earlier in the slide. The different lines correspond to a bunch of different algorithms. The ones that you want to focus on are the first 2, blue and yellow, which is 2 instantiations of our GPL algorithm. And then we have all kinds of baselines and ablations. Again, in the interest of time, I'm just going to skip over the details here. But what you can see from left to right here, in this case, there's a few algorithms that achieve near optimal performance, but then as you get into the more complicated tasks, you see that we take off with the blue and the orange line here. And this is already an indication that the ability to sort of resize the value estimates gives us a useful benefit here. The more interesting part of the evaluation is post-training. So this is within training, and now we want to see the GNN model's ability to still give us meaningful value estimates when we now take the trained model and deploy it in a system or an environment that it hasn't been exposed to during training. So now we tested it. We tested in teams of up to 5 agents. It really can change the role that you need to assume within the team, right? And again, we have a table here where we have the 3 environments in the rows. We have the various algorithms here in the columns, and our 2 algorithms are highlighted in bold here. You can see achieve a large margin compared to these various other algorithms. So despite the fact that training is finished, we see that these the ability to resize basically gives us and the way in which we integrate this with the predictions given by the agent models into the value estimates gives us the benefit here to still adapt to these situations. We have various ablations here as well of the same method that take away bits and pieces basically, but whenever you take away one piece or another, the method breaks down basically. So it really shows that this particular combination of how we integrate agent models with the value estimates gives us something useful here. And so this gave us the confidence that this was worthwhile pursuing, and we have done a lot of subsequent work that's under review at the moment at a few places. For example, trying to also make this work in environments where there's very significant partial observability. Okay, this was the first category of work when we control a single agent. I just want to wrap this up with one slide in case people want to learn more about AdTalk Teamwork, which is this bigger problem here. At ICHGAI, which is one of the main AI conferences, ICHGAI last year, we organized a workshop on AdTalk Teamwork, and I know Matt was there too. Matt was one of the invited speakers. We had a few speakers there, including someone else from DeepMind as well. And this covered various topics related to AdTalk Teamwork, including agent modeling, zero-shot coordination, and so on. And also shortly after, we published a survey paper, I believe the first survey paper about AdTalk Teamwork. And that came out last year. So if you want to learn more, you can see a screenshot of the authors here on the lower right corner. You can have a look, and please get in touch if you have questions or if you have interesting ideas. Good. So now I'm moving to the second category of research. Now we control all of the agents in the environment, not just one guy. We control the entire team, and we want to create reinforcement learning algorithms that enable this team to learn collectively how to solve the task that it's given. And in this particular piece of work, we're interested in multi-agent tasks that are characterized by what we call sparse rewards. So this means that there isn't a meaningful sort of reward signal at every point in time. There might only be a sort of a non-zero reward signal at very few points in times. And in the worst case, there might only be a non-zero reward signal at the very end of the episode when you actually solve the task. And until you get to that point, there might be many decisions that take you to that particular point. And then you're faced with the question of how you backpropagate this, and then the well-known credit assignment problem. So here we have 4 examples that we actually use in this work. There's on the left, you have a sort of a toy version of a warehouse problem where you have these agents that need to work through orders of collecting and delivering sort of items. And they only get non-zero rewards when they manage to achieve that. So when they actually pick up and deliver the correct item and then bring it back, which involves, in some cases, tens or even hundreds of decisions. Then we have a sort of StarCraft 2 micromanagement task where you have 2 units of Marines that need to shoot each other down, and various other coordination tasks. All of them are characterized by the fact that we require teamwork and there's sparse rewards. And by the way, this was published, I think, 2020 at NeurIPS. And again, we've done subsequent work, but I still like to present this work because it's a very simple method that gives some really strong results. So here we use multi-agent reinforcement learning, and I'm just giving this one slide to explain what it means, although I assume that most people will be familiar already. We start with an environment, and these examples that I showed earlier, that would be all software-defined environments. And we have our agents. In this case, it's a fixed team. We have exactly n agents, and it doesn't change. Every agent gets an observation from the environment, chooses an action. The combination of these actions is what we call the joint action. That's then passed through the environment. It changes or affects the state of the environment, and then you get a new observation and you get a reward. So that's essentially just an extension of the standard RL loop, except that we have n agents, and they choose actions, which are then passed to the environment. So we use this loop basically. This is the multi-agent reinforcement learning loop. And the naive way of doing this is what we call independent learning. And basically, we're actually building on independent learning. We just add a twist to it that makes it a lot more effective. The method that we propose is called shared experience actor critic, or SEAC. And I'm showing this toy example on the right to explain what we're doing here. So let's say there's a grid well task where there's these two agents, and their goal is to arrive at the center block here, the gray one. And only then do they get a non-zero reward. So it looks like a really simple toy task, but it's surprisingly hard because you have a combinatorial search space here, and they can do a whole lot of decisions. And only at some point do they reach the center, and then they get, for the first time, a non-zero reward. So they have to make sense of this then. Let's say they explore and they produce these trajectories, which are shown in the dotted lines here, and then they get to the center point. If you use standard independent reinforcement learning, you basically just use off-the-shelf existing single agent reinforcement learning, and you train each agent independently using their own trajectory that they produce. So in this case, let's say we update the policy for the blue guy. We have produced this trajectory, and we use that to do our backprop, and then we update our policy. So the question we have here is, why don't we also use the data from this other guy when we when we construct a gradient to update this guy's policy, right? It kind of seems like a wasted opportunity not to use that data if it's a teamwork task like this. So that's basically what we're trying to do here. So the only thing we change here now is the way in which we produce the local policy gradient. We don't change anything about the architecture. It's just the same independent learning architecture. We don't add anything fancy to that. We also don't make the algorithm more complex. The only thing we do now is, when we compute the local policy gradient for this policy that we're updating, we also use the trajectory that was produced by the other agent. We're reusing this data as if it was produced by ourselves. And because it's now off policy data, it was produced by, in fact, a different policy, we have to add an importance sampling step. And then we integrate that into how we calculate the policy gradient. That's all we do here, basically. We don't change anything about the actual architecture. Mathematically, it looks like this. So if we have the standard policy gradient would be this here, shown in the blue box. The only thing we add to this, or subtract more technically, is the local policy gradients computed from the trajectory of this other brown agent here. And we also add the importance sampling step, which is shown in the box here. So these are all well-known existing techniques, right? So the policy gradient here is exactly as above, except that we use the data from the other agent. And the importance sampling is also just standard importance sampling. We use the most naive type of importance sampling you can actually do. There's a lot more sophisticated ways of doing this. And we combine this with the original way of calculating into the gradient that's already calculated up here in the blue box. So the intention is that with this added data, we produce more robust policy gradients. Here are some results. First, we tried this in all kinds of tasks. I'm just showing a subset. In this case, we have the warehouse environment with this particular configuration you're seeing here, with four agents that need to collect these different shelves, bring them to the workstation, and then return the shelves. And in this set of examples and results, we compare three different algorithms. The green line is SEAC, which is ours. And then we have two baselines. The orange line is SNAC, which stands for Shared Network Actor Critic, which means there's one policy network. Everyone uses the exact same policy network and also trains collectively the same policy network. So they naturally use the same data, all the data to train the same policy. And then the blue line is independent actor critic. So it's just everyone uses their own independent actor critic, and they don't use the data from the other agents. The four plots I'm showing here correspond to increasingly complicated versions of this task. So you increase the number of agents, or you increase the size of the environment, and it just basically gets more difficult. So what you see as you go more difficult, there's an increasing sort of a margin of improvement here between our method, which is green, and the other methods. And there's some really interesting analysis you can do, and we show some interesting things in the paper. But just a few things to highlight here. One thing is, you might ask, how come shared network actor critic loses out so much, even though it also is based on the idea that you use all the data to train one policy. Well, the problem here is that because they in fact technically use the exact same policy, they don't have the ability to learn differentiating behaviors. So in some situations, you end up in a situation where one agent has to take one particular role and the other agent has to do some other complementary role, but you cannot represent this if they use the exact same network. So what you tend to observe is you have slightly faster transient performance initially because you have more efficient training, but then you quickly reach your plateau because you don't have the ability to differentiate. Whereas in our case, because we do have independent networks, they can still learn these differentiating behaviors. Now, if you compare them to the blue line, you could also ask, well, how come the blue line isn't catching up to the green line? Because it does use the independent networks, but it's, as expected, it just takes a little bit longer to get there. Why is there still this limit difference? Well, there's a really interesting sort of phenomenon we observed in this work, which is that if they learn completely independently, and in particular in these sparse reward environments, it can often be the case that one agent or a small subset of agents gets ahead in their learning over the others much sooner than the others. So when one agent becomes really competent early on, sometimes it can be that this agent deprives the other agents of important experiences that they require in order to catch up. So this is non-uniform learning progression that can actually stabilize into a really bad local optimum. In our case, this doesn't happen because they all always share their data, which means there's sort of approximately a uniform learning progression. So it's really interesting sort of learning dynamics that we observe there. And we talk more about this in the paper. More results. Here's the StarCraft environment. Again, the same other baselines. They completely fail to learn here, and we learn here successfully. Here's a comparison with some more state-of-the-art methods. For example, QMix, MIDDBG, and Roma. All of these three methods are very significantly more complicated and more complex than our method. They have much more complicated ways of computing gradients. They have much more bigger blown up network architectures. And they're also much more difficult to understand, to make sense of. But still, in all of these difficult tasks, we actually either outperform or perform equally well to these other methods. In most cases, we actually outperform them. So it's kind of an interesting situation. You can ask questions, how come they don't perform well? And we give lots of sort of insights in the paper. But it's also sometimes an indication that the knowledge we produce in this space isn't super robust sometimes, and we have a lot of thoughts about that. Okay, so this is the paper in the second category, when we control all the agents. And again, I just want to wrap up with one sort of resource slide. If you're interested in multi-agent RL, we have a blog, which you can find here in the URL. We have all kinds of posts where we talk about problems that we find in this space and also sort of information to get you started. There's one blog post in particular that has been making the rounds about that I actually wrote about common inaccuracies that I've observed in multi-agent RL, in particular in the more recent generation where all the deep learning got into the community. And also other blog posts, implementation tips and tricks for DRL. There's a lot of stuff you need to know. And sometimes the implementation tricks are more important than the actual claimed contribution in the paper. So it's really important to be aware of this. Then we have code repositories, which are actively maintained. The most important one to point out is our multi-agent RL code repo called Extended PyMRL. This is actually based on an existing code repository from Shimon's lab at Oxford, and we actually have standardized a lot and made it easier to use and made it compatible with an OpenAI gym interface and added all kinds of things just to make it more usable and integrate more algorithms. So this has been picked up quite a lot. I think it has nearly 250 stars now on GitHub and was published, I think, last year or the year before in NERPS. So please have a look if you want to get into this space. It's an easy way to play around and get some initial results. And lastly, just to announce that I'm actually working on a textbook about multi-agent RL. This will be published with MIT Press, and it's nearly finished. And so hopefully will be published in the summer months this year. So it's well underway. And if you want to get updates about the books or anything else, then please sign up on Twitter. Okay, so this is the first half of the talk. I think I have a few more minutes because we started late to talk about the second part. So the first part talked about the work we do at the university group, but also do a lot of work with companies and industry. And there's one company in particular called 5AI, which was founded in the UK, and that's about self-driving cars. So let me tell you a little bit about that. 5AI was founded in late 2015, and quickly became a leading AV startup in Europe. So AV stands for autonomous vehicle, but basically means autonomous driving. The idea or the vision was to build a complete technology stack for autonomous driving, which includes tasks such as perception, planning, prediction, control, and later years we also have put a lot of effort into building simulation and testing infrastructure. We were the lead partner in a very large, substantial urban road trial, which was conducted in London over a long 20-kilometer route, going just back and forth all the time. And all kinds of challenges you can imagine existed in this space. And this was in London, which has a lot of really weird layouts compared to the US. And the company was acquired by Bosch last year in a big deal. And now together with them, we're Europe's largest level 4 autonomous driving company. On the upper right, you see one of our fleet vehicles that was used in this trial in London. And the company itself is actually a multi-agent system, basically. So we have offices in different cities in the UK. The office that I work with is in Edinburgh. We specialize in motion planning and prediction. Other offices specialize in other tasks like perception, control, simulation testing, and so on. We use a large test track just north of London in Millbrook. Okay. So here's the vehicle that we used in the trials. This is actually outdated now. This was from a couple of years ago, but I'm showing it anyway because it looks cool. So this is an existing Ford vehicle, but we tuned it up to make it self-driving capable. So on top of the vehicle, we created this sensor box, which has all kinds of sensing modalities in it, including different LiDAR and radar types, stereoscopic cameras, and pointing in the different directions. The whole boot was stuffed with compute, and we have all kinds of monitoring equipment inside. There will always be 2 drivers, one safety driver and one sort of safety engineer, who try to make sense of the data feeds as the vehicle is driving. Here is a video of the vehicle going in London. So there's the safety driver here. It has to be there, but it's not actually touching any controls in the vehicle. And then left of him is another safety engineer looking at all the data. And you can see basically driving around. So if you ever get the opportunity to drive in a self-driving vehicle, and if you trust the manufacturer, then it's a really interesting experience. I can really recommend it. Here's the same route and the same driving, but from the vehicle's perspective. So now at the top, we have a fused state estimate that takes the different sensing modalities into one place. And at the bottom, you have 2 camera feeds, one pointing forward and one pointing to the right. And you also have the planned trajectory as an overlay in a video here. So you also see the detections of the other actors. We've approached a roundabout here. There was an opportunity to go in, and then that's what we've done. You can see how we're tracking this local trajectory here. There was also a zebra stripes, but no persons waiting there, so we were able to just continue. So it's a very complicated task. There's a lot of stuff going on. There's a ton of data that's coming our way, and we have to make sense of this very efficiently. We have this pipeline approach of thinking about this, which is basically to decompose this sort of task sequence. Begin with sensing and fusion, which means we have these different sensing modalities. We fuse them into one big global estimate. We then have localization, which is the task of understanding where we exist within the space. If you don't get that right, you can't do anything else robustly. Detection is detecting the other dynamic and static actors and obstacles. You have tracking, which is once you've detected someone else, you also want to be able to track where they're going. And one of the difficult tasks is here that you don't want to mix them up with other actors, especially if it's a really dense environment. Prediction is the task of making statements about the future sequence of local states of these other vehicles. And planning takes all of this information into account and tries to come up with a sequence of maneuvers to get us to a target destination. So we're talking about maneuvers like change lane left, continue straight, turn left, give way, and so on. Whatever we've planned is then ultimately compiled down into the lower level control layer. So your plan is compiled into the lower level controls like steering and braking. My work in particular is in prediction and planning with the Edinburgh-based office, and we also do a bunch of work in control. So one thing that's really cool about this company is that they have a very research focused portfolio of work. So the Edinburgh-based office does a lot of work in motion planning and prediction. The other guys in the different offices may work in others research problems. So I'm just going to talk you through some of the work we do in the Edinburgh-based office, which is about prediction and planning. When I talk about the work, I like to kind of classify this into 4 different categories. We have trajectory prediction, which is a very well-researched problem, but super important and still a lot to be done. Goal recognition has received less attention, but we feel that it should receive a lot more attention. So that's why we have done a lot of work in this space too. Goal recognition is just I guess you can say, a more longer-term version of trajectory prediction, where you're trying to make sense of their ultimate sort of intended goals. Optimal planning, again, is an important task when you have a dense environment with very kinds of structures and constraints, and you want to have a sequence of local controls to get you to drive safely through this environment. And we also have a focus on producing systems which could be called interpretable or explainable. So we can actually make sense of what's happening here, and in particular in safety critical environments. Here's a few papers that have come out or under review in these different categories. And we also started a collaboration with NVIDIA in the Bay Area, who want to get into the space too. So, of course, I don't have time to talk you through all of these pieces of work, but there's one example, maybe 2 if I have time, but let's say at least one I'd like to tell you about. And that's in the goal recognition category. And in particular, it's a system called interpretable goal-based prediction and planning for autonomous driving, or IGP2 for short. It was published 2021 in ICRA, which is one of the annual flagship conferences for robotics. So what are we trying to do here? We want to have a complete integrated system that does both planning and prediction and also control. And we have a certain set of properties that we want to fulfill here. We want to have a system that is safe, so minimize crashes. We want to have a system that effectively gets us to the target location. We want to have efficient driving, so when there's an opportunity to cut driving times, we want to be able to exploit that. But also we want this to be explainable, right? So we want to be able to look at the system and then make sense of why certain predictions were made and how those predictions affected certain choices that were made. So here's an example to explain what I mean by that. Let's say we are the blue vehicle. We're coming from the south here, and our goal is to turn left towards this goal named G1. So let's say we're sitting in this vehicle, and then we observe these other vehicles going around here. And now let's say the vehicle has decided to merge in here and just turn. And this might be surprising, right? You could say, hey, what's going on? Why did you just turn left when there's all this other stuff happening? So we would want to be able to ask the system a question like this, or at least we want to be able to look into the system and try to find an answer to a question like this. And ideally, the kind of response we want to get is something like this. The vehicle could say, well, I've observed that there's this vehicle number 2 on the right that has stopped. And the only way for me to explain this behavior is the fact that it wants to turn right, because if it wanted to continue straight or turn left, it could have just done so. It would be highly irrational for it to stop in the middle of the road. And so if that's the case, I also know by extension that it will remain stopped for a while because there's this traffic coming from the left. Let's say there could be even 10 vehicles coming up. So there's now a window of opportunity for me to merge in here and turn left. I don't have to wait for this entire situation to resolve. And that's why I chose to do that. So that's the kind of explanation that we want. It's easy to understand, and it's sound, and it's nearly essentially complete, right? Certainly the kind of explanation that I would give in a situation like this. And in this particular work, we're trying to develop a system that actually gives us the foundation to produce these kinds of explanations. In fact, we are working now on a prototype that actually builds on the system, where a passenger can really talk to the system like I've just done and ask this exact kind of question. The system understands the natural language query, looks into its own reasoning, and then produces a response to the query that is synthesized in a natural language and then produced back to the user inside the vehicle. So I think in the longer term, the vision is that we really need this type of interface to enable a user to gain trust into what the system is actually doing, and to be able to gain the trust, but also for debuggers, right? If something goes wrong, even a debugger could make sense of this kind of information. Right. So what's IGPT doing? It's kind of a relatively complex system. There's a few things that come into play here. I'm just going to give you some high-level parts, and some parts are more interesting than others in terms of the science. So let's start with the plan library. This is the language we use to basically define what actions the different actors can take in the environment. So we have two layers here. One is the basic maneuver. These are the things that we know when we see them, like follow lane, change lane, turn, give way. So there's already naturally labels attached to these kinds of actions. And then we have macro actions, which basically just concatenates these basic maneuvers to get a sequence of basic maneuvers. In this case, we have an example for exit right macro action, which concatenates follow lane, then giving way, and then once the traffic is passed, you go into the last maneuver, which is to turn. So the idea is just to keep the depth of the search a bit more, to reduce the search depth, because this is a kind of domain knowledge that we robustly produce, and we want to be able to integrate that into the system. We don't want to burden the planner with redetecting this kind of sequence every time. So this is the plan library. More interestingly, how do we actually detect what the other actors are up to? And that's where some of the more interesting things are happening. So goal recognition is the task here. We want to, based on the observations that we've made about the other vehicles, understand what they might be up to in the longer term. The first thing we need is a way of producing the possible goal hypotheses. In this case, we can easily extract this from the local road context and from the local state of the vehicle. There's really only these three goals that they can possibly want to reach. So let's just assume we have something like this. More interestingly, how do we then make sense of the probabilities over these possible goals? And here we use a technique called inverse rational planning. Basically, it means we put ourselves into the shoes of this other vehicle and we plan on their behalf. It's a Bayesian approach. We have, you can see in the first line here, a posterior that we calculate, which has a likelihood component and a prior over goals, and a likelihood of observing a sequence of local states, given the assumption that you want to reach that particular goal. But more interestingly, how do we define the likelihood? The likelihood is basically takes the difference of two reward calculations. And I'm going to give you the high-level description. Two reward calculations. The one on the right is the reward that this vehicle would receive when executing the optimal plan from the very first state when we got to observe this vehicle, right? So technically speaking, the best you can do to get to this particular goal. We take that from the reward that we would get for a plan that continues optimally onward from the current state of the vehicle that we have observed to the current point of time. So the idea is that the closer these two reward components are, the more rationally this vehicle will have behaved, and then that translates into a higher posterior. On the other hand, if there's a big discrepancy, we say that it was irrational behavior, and that translates into a lower posterior. So as an example here, let's say we want to get the posterior for the vehicle to going straight. Going straight optimally from the very first moment when we observed it, let's say here, would just be a constant velocity at the speed limit, right? But here, now we've observed the vehicle stopping. And if we now plan optimally onward, we have to now re-accelerate to the speed limit and then continue. So this incurs a penalty in terms of the smoothness of the ride and other reward components. So there would be a discrepancy, and we say this was irrational, right? So it translates into a lower posterior. That's in a nutshell, the idea here. And this then goes into ego planning, this kind of prediction information, including trajectories that we predict and associated probabilities that I'm not going to talk about just now. What does ego planning do? Ego just refers to the vehicle that we control. And here we use a type of reinforcement learning called MCDS, or Monte Carlo tree search. What does it try to optimize? There's two parts in this here. We try to find a policy that does a trade-off. The first thing that we're interested in is the probability of success, or minimizing crashes. And we're trading that off against the quality of the solution. We don't want to just minimize the crashes. We also want to produce a comfortable ride. So there's various parts that play in here. So for example, trajectory execution time, we want to have smooth rides, path curvature, and longitudinal and lateral jerk, and so on. So there's the quality that we're trading off with the probability of success here. So basically that's just the objective. I'm not going to go into the details of MCDS. It's basically reinforcement learning. We've done experiments in quite a few different settings. first round of experiments in 4 fixed frame environments where you basically just act in this particular scenario that we provide here. Scenario 2 is the example that I showed you earlier, and there's other interesting scenarios that require various kinds of interactions. The last one here is quite interesting. There's a vehicle that leaves a gap ahead with the intention for us to merge in. And we were, I think, the first paper that actually solves this. And not only do we solve this, but actually we do this in a way that we can make sense of, which I'll show you in just a second. First thing we want to establish is, does our way of recognizing the goals of the other actors, is that sound? And the way in which we test this is by trying it out in all of these environments. The different colored lines correspond to the different environments and also different vehicles. We have on the x-axis the time. So as we increase the seconds, we get to observe more data, more local trajectories. And then on the y-axis, we have the probability, the posterior, assigned to the true ground truth goal, which we know in this case because it's simulated. And what we want to see is that this consistently goes up to 1, right? So it tells us, okay, we understand ultimately where the true goal is. So this is what we observe in all of these examples. In fact, we even observe this in versions of these environments, which are where there's very significant occlusion. So these are the dashed lines. In this case, we take away big segments from the observations, and the method just has to deal with that, which you can with pretty much the exact same approach of doing it. So it's a robust way of detecting goals. The next question is, well, once we've detected the goals, does that enable us to improve our driving efficiency? And so as measured in terms of seconds. We have the 4 different scenarios here and various kinds of predictors. Ours is the first row here, and you can see that in all of these environments, we actually solve them faster, and in some cases there's quite a big difference. You might think, well, 4 or 5 seconds is not a big deal, but actually it racks up quite a bit if you have a big town and then you encounter many of these situations. You want to have a vehicle that can efficiently identify these opportunities to cut driving times. Here's an example video that shows you this last scenario where that I explained. And this shows you the 3 different steps between prediction, doing the planning or MCDS, and then executing the planned maneuver for a particular amount of time. So you see that these colored bars here, which correspond to the goal posteriors. And as we unfold the situation, we can understand that the vehicle at the bottom here, its goal is basically for us to go in here. And that's what now unfolds in the next step in the MCDS planning here. So we detect this opportunity and we safely merge in here. And what's really useful about this method is that we can actually look into the inner workings and we can understand every single step in this pipeline. We know exactly why this prediction was made, and we can then understand why this prediction affected the choice and basically how that choice came about. With the deep learning approach, I have not seen a deep learning approach that solves this robustly yet. But even if it does, it would be essentially impossible to make sense of why it decided to do this. And that's a really important aspect here, that we want to close that gap. We want to make sense of why choices are made and even translate that in a way that a user can make sense of. Right, here's the same thing, but over a whole sort of a town scenario where you have many of these situations. We compare it against the conservative baseline, which is the yellow one. And you see now there's quite a significant difference in terms of the seconds. But I'll just continue on in the talk here. Right, so just to wrap up that paper, because this was built at a company, we weren't able to open source the code there. So I've tasked a few guys in my group at the university to actually reproduce the code and make it open source. And on the way, we also made it compatible with a large, widely used simulator called Carla, and also using existing standards like OpenDrive. So everyone can use this and play around. We also have a blog post. If you want to play around with this, then please check it out, and also feel free to get in touch if you have any issues. Okay, some extra work building on this, but I think I've kind of run out of time. We started a bit late, but I think I should leave some time for questions. So there was another paper here. I'm going to skip over this. This uses more real data and deployment and verification. Just one more minute to point out something else. Just the last 2 slides. In the UK, I've been involved heavily in an initiative that is organized within the Turing Institute. Turing Institute is branded as the UK's National AI and Data Science Institute. This is the joint work I've been doing with Michael Rudrich at Oxford. And the idea is that the UK historically has been a really big contributor in multi-agent systems research, but over the years became really fragmented, and then it was kind of hard to see who's who and who's doing what. So we wanted to have a national meeting point to sort of map out the landscape of existing work and see who's doing what. So we started off with this really successful symposium. Then we created this virtual labs map on Google where we pinpoint all the major players, including in defense and industry. We have this online talk series you can check out. I think it has now 14 or 15 talks by some major labs, including Huawei and DeepMind as well. And most recently, we had a special issue, a journal issue published, came out last year. And that includes articles by, again, the sort of major labs in the UK that operate in the space, including also a paper by DeepMind. And so these papers describe the research agendas in multi-agent systems research. Okay, so that's me now finished. Thank you very much for your attention. And hopefully we have a few more minutes to go through questions.
Thank you, Stefano.
Matt, I'm seeing you said hockey again. I'm not sure. Is that a question or a request?
Not yet. Does anyone have any questions?
I'll ask one, Stefano. You gave a pretty broad overview, and so now I'm going to do an overview-like question. Where do you think where's the next challenges that if like a new student wanted to get involved in doing some multi-agent systems and more multi-agent RL, what do you think are like the core challenges that the field are facing that we don't know how to address right now?
Yeah, so I have a few thoughts about that, and I guess I should limit myself. But one thing that I'm increasingly paying attention to is to make sure we understand what kinds of outcomes we want to achieve in the first place. And I feel there needs to be a conversation where we talk more seriously about the different kinds of solution concepts and whether or not they're meaningful in particular situations. Certain solution concepts have been kind of adopted as a more or less a standard with where I feel there's a lot of problems and limitations that aren't really discussed in the community. So I feel a lot more time could be spent talking about the foundations and really what it means in the first place to solve a multi-agent system and for agents to act optimally. So I feel it's a really important question that should not be underestimated. And then there's various sort of satellite problems that come out of this. How do you solve a particular type of solution concept? I think there's a lot of questions to be asked about producing systems that are robust. Like brittleness is just a really important problem in reinforcement learning. Has been for a long time, but in particular with the deep learning sort of incarnation. And I think, yeah, so those are some questions where I feel a lot can be done.
Cool, thanks.
How do you feel about that, Mike? What are your big problems?
I agree with your first one. I think I don't know if you've seen a talk I've given where I've been pushing that our concept of like things like Nash equilibria are maybe holding us back. And I think it's like the way I've been describing it is artifact-based solutions versus like artifact-based descriptions of what we want, as in I want something that learns a policy and then I care about the artifact that is the policy. I think it's more important about behavior and change. And that's a harder thing to think about. And so like, I agree with you. I think getting the foundations right. I mean, the funny thing is I think that statement that you said could have been true about multi-agent systems 10 years ago and could have been true about multi-agent systems 20 years ago. And since I've been in the community, there's always been this tension between we can go and build stuff, but do we understand what we're building? And that's been a constant tension.
Yeah, I try to reflect that in the book too. So there's a substantial part initially that really just talks about what it means to solve a system and the various kinds of approaches there. And of course, the book also includes quite a bit of your work too, which influenced me a lot when I was a PhD student myself, and really like your works a lot there. So it was a nice experience to go through these memories again as I prepared myself to write the book and remind myself of all the stuff that I re-implemented from your papers and so the sort of inspirations I got from your work. So yeah, this is really a nice process.
Thanks for the kind words.
Right. I just want to say again, you know, if there's questions coming up later, feel free to reach out, please. I'm always happy to chat with people. And if you want to try out the stuff and maybe something doesn't work, feel free to get in touch. And people in our group are always happy to talk with everyone, help them get their code to work.
Do we have any final questions? We have one question. You want to come up here and ask?
Oh, yeah, sure. So you said like one of the primary goals in your machine learning car or your self-driving car is just getting to a destination quickly. But I can think of several scenarios in which that it's possible or it's arguably reasonable to not quite do that. Like if someone wants to merge in front of you. So like, how do you
no, just to say, I don't think I actually said that. I was careful to say that it's a trade-off between various components. So there's the higher level is the trade-off between the safety or minimizing crashes, which is a core component, and then the solution quality. And the solution quality itself is sort of quantified as a combination of different factors, basically smoothness of the trajectory and other elements. So the trajectory execution time, which is just one part, is what you're referring to, but there's all kinds of other elements that play in there as well. And safety is almost like an overriding criterion there. So it's not the case that we're building a system that just tries to be as fast as possible. That would not be acceptable.
Right. So if you're keeping safety into account, let's say you see a car wants to merge in front of you, how do you, like, it doesn't benefit you to let them in. It only benefits the other person. So how do you kind of accommodate for this benevolence? Even if you take safety into account, you can let them just go behind you and merge in behind you. Right. So do you even take that into account?
I'm not sure I understand the question. So let's say there's a vehicle that's stopping to leave a gap in front, but that's not the ego vehicle. You're saying, why would the vehicle do that in the first place? But that's not the vehicle that we control, right?
Right, but you have the option to let them in front of you, or just let them have to keep slowing down and go behind you. So do you just...
How do I have this option if I don't control that vehicle?
Stefano, will your car ever leave a gap to allow someone to merge in?
Oh, I see. No, we didn't actually. No, the system would not do this. We have not provided for this kind of capability because we haven't designed environments to test it in this kind of space. But it would be possible. We can code that in. Now I see what you're asking. So now you're saying if our vehicle had we switch places, and the question is, would it ever make sense in our system for another vehicle to allow it to come in ahead? I think. I'm not quite sure what the answer is. I would have to think more about this. But quite possibly the system might be a little bit selfish because there's no component there that quantifies sort of a fairness aspect. And there's a lot of work in this space that tries to quantify fairness too, with different kinds of approaches. That's not really something that we thought about much in this particular work here. We had different focus on the interpretability aspect, but it's an interesting question. And we have one work where we do multi-agent RL for autonomous driving, and fairness is a really big deal there, creating solutions that benefit sort of a collective, not just an individual.
Thank you.
Yeah, thank you too.
Okay, thank you very much, Stefano, for your great talk. And if anyone has any questions, reach out to you.
Have a good weekend. Bye-bye.